Good afternoon, everybody. We are going to start. So let me start, and I'll introduce this very, very important panel, the moderator for this panel. In the morning, I told you that we picked a very bold theme of this conference, from knowledge to innovation. And there are certain classes of innovation where knowledge actually is the raw material. These are the deep techs, or the hard problems. These innovations are, generally are not funded by startups, by the VCs necessarily, because the 7-year horizon doesn't match. Some of the innovations, as you know, may not have a schedule. So you need a special type of VCs. And these are, when you say deep tech or hard problems, when you say these things, first thing comes to your mind is, what kind of problems are these? In our language, we always say that, hey, that's a rocket science. That's not a rocket science. So these are those rocket science class of the challenges that we solve. And we, being engineers, we wanted to have a session on these deep tech. And I told you that we have been curating speakers, and we're looking for one. So Nidhi told me, for this session, go and get with some background in physics, because, these are the physicists, as Dr. Anima Anandkumar told us in her speech from Caltech, that how AI is helping those type of problems to solve. So I said that, Nidhi, in my several decades of career, I never had a VC who is from necessarily the physics world. Now, but I did remember once it happened. I was in a startup with a NEA who was in the board, and NEA, one gentleman gave me a card, and I saw that Dr. Arno Penzias, Nobel laureate. So it does happen sometimes. So we are looking for somebody who comes from the physics background and who is also part of the corporate VCs, CVCs, that actually pair these startups, the deep tech startups, with a built-in design partner. And I told you that when you think of rocket science, you think of NASA, and also have worked in the NASA. So we are very lucky to have her. So please welcome Dr. Geetha Dholakia, who is from the TDK Ventures, who is a physicist. She has a PhD in physics, and who has spent 4 years at NASA managing some of the $200 million SBIR program and so on, and now guiding many, many deep tech startups. And she is also bringing the managing director of Samsung Ventures. She's also bringing the portfolio, the investor director from TDK Ventures, and also a sample startup who is solving the in-memory computing problem for preventing this memory wall in the inferencing engine. Please give a big hand to Dr. Geetha Dholakia.
Good afternoon, everyone. I hope you had a really nice chai break. So we're going to shift gears a little bit here. You've heard a lot of great presentations this morning about the software space, but we will now shift to hardware ecosystem. So let me first have a couple of minutes to introduce our panelists. Would you start, Ankur?
Yeah. Sure, happy to. Hey, everyone. So I'm Ankur Saxena. I'm an investment director with TDK Ventures and a proud IIT Kanpur alum. I joined TDK Ventures recently, spent 9 years at Cisco Investments, also covering AI, cloud, and infrastructure investments. At TDK Ventures, I spend my time leading investments in AI, compute, and connectivity. Nice to meet all of you.
Hello, Vishal.
Hi. I'm Vishal Sarin. I am founder, CEO of Sagence AI. We are really building a core technology that is essentially, you could call it compute in memory. My background over the last 30 years has been in semiconductors and systems, but more specifically in memories, both volatile and non-volatile, in-memory compute architectures, network processors, and such. And excited to bring to boot what we've been building for the last several years, because I think it's really something that we need. The industry needs to solve the power efficiency problem for AI. Thanks.
Siddharth?
Good afternoon, everyone. My name is Siddharth Gupta. I'm a managing director at Samsung Ventures. Samsung Ventures is the corporate VC arm of the Samsung Group. Prior to Samsung, I spent a dozen years as a chip designer and chip architect at companies like Apple, NVIDIA, and Maxim. And a few years ago, I transitioned over to venture investing, where I focus on investments in robotics and semiconductors, and I have to say AI, because you won't take me seriously if I don't, so AI as well. Thank you.
Thank you for the panelists. So Silicon Valley, as we know, has for long been known as a hub for software innovation, but that's starting to shift a little bit. Today, we are seeing a growing number of venture capital firms, as well as corporate venture capital firms, turn their attention to deep tech and hardware-focused startups. For CVCs, that is the corporate venture capital ecosystem, this space actually aligns very directly with their strategic priorities, allowing them to contribute more than just capital to the startups by bringing in technical expertise, manufacturing capabilities, supply chain access, and more. So when the organizers, like he was just mentioning when he was introducing me, Ashish, we were thinking of what would be a good panel to put together. One of the themes I wanted to highlight was this hardware ecosystem for AI, which is how we landed with the title, Matter Matters. So with that background, let's go to our first question. Ankur, let's start with you. As AI workloads evolve, do you think we'll continue to rely on GPUs and CPUs and TPUs, or are we reaching a point where alternative computing architectures, such as neuromorphic compute and other specialized architectures, could become more viable at scale? It will also be helpful for the audience if you can give a quick overview of these different types of architectures and share your perspective on whether one or the other is better suited, say, for the cloud or for edge compute.
Sure, happy to. So to address your question head on, I think over time we will see diversification in terms of the kinds of architectures that data center or other enterprise users would deploy in their compute requirements. So far, GPUs have performed really well in terms of 3 Ps, which is power, performance, and programmability. But over time, customers, as their needs, as their workloads become more diversified, as they achieve mass scale and adoption, I think the requirements in terms of the compute will evolve along these 3 Ps. Talking about the 2 broad ends of the spectrum, data center and edge. So data center first. Data center, I would say, in the data center, rack scale is becoming the new compute unit, and customers are looking to optimize power, performance, and programmability at the rack level, not at the chip level anymore. And I've seen 2 distinct approaches here. One is companies like Google that want to do all of this in-house in the form of TPU platform. And then there are other companies like Meta and some of the other hyperscalers that are building some of it in-house, but also mostly partnering with specialist vendors to build custom solutions. And that is where ASICs, or these application-specific ICs, or accelerators, the ones that Sagence or Grok are building, would become adopted in a big way, because they offer better price, better performance, better power, and programmability. And on the other side of the spectrum, which is edge, power or performance per watt becomes the key KPI to optimize. And that is where GPUs underperform some of the custom ASICs that optimize for effective TOPS or effective performance per watt. And that, I think, is a very massive area of growth for startups especially, because that's an area where Google, TPUs, or GPUs will not work. And that's where I think neuromorphic approaches, which are way more power efficient, can actually make a meaningful impact. But where these approaches really need to stand out are they need to be as programmable as an NVIDIA CUDA. Right? CUDA has been the significant software moat for NVIDIA and has generated significant stickiness for them. For neuromorphic and some of the other innovative approaches to beat NVIDIA or other incumbents at the edge, I think programmability will be key. So that's my perspective. Vishal, anything to add to that?
Yeah, no, that's absolutely right. I think you pointed out, hit the nail on the head. I just want to add a little bit to it. If you just now go a little deeper into the edge landscape, there are a lot of verticals in the edge. There are sensors, and the sensors would require microwatts of power with very small neural networks attached to them running. So that's a very different requirement in terms of power, in terms of performance that's needed. There are cobots, now humanoid robots. These have different sizes of models that need to run. They have different requirements in terms of performance, and they have different requirements in terms of power consumption. Now, also, by the way, in terms of economics, in terms of you can't build a high-performance processor with very low power and then sell it for $100 when the bill of materials of a robot or a retail drone is just $50. So you have to look at all the axes of what you're trying to build when you go to market. So to that end, I would just break it down. There's very low power applications, and they are typically very low cost applications as well, like sensor attached applications. Then you move on to cobots and robots kind of applications where the model sizes now are not sub-million parameters, but rather a couple billion parameters, requiring larger performance levels. Now, the power consumption there is not driven from the cost of power or the ability to deliver the power. Is driven from, a lot of times, battery requirements. So the battery requirements dictate, if you have a humanoid robot, how long that robot has to kind of work around without having to recharge it. So the requirements are different. If you look at a robot, 30% of the power is coming from your compute platform. The rest, 70%, is coming from actuation and movement of arms and stuff like that. So the need for what kind of trade-offs you will make in terms of amount of compute, what about the power that it goes with, and the cost. These are three very key axes that you have to look at when you're trying to go to market there. Data center has become a huge impediment for power consumption, very big, because models have really grown. Language models, which are essentially what data centers at a fundamental level run, they have grown 4 to 5 orders of magnitude in the last few years. So that means the compute requirements has really shot up, power requirements have really shot up, and this is, there's this issue about generation of power, delivery of power, which is very concentrated now, 100 megawatts in just one building, and then cooling infrastructure. So big impediment for the industry, and there then you don't have such a constrained cost, compute cost. Compute cost is, it's 88% of your CapEx in an AI data center is compute and memory, which is huge. So you can imagine $100 billion that Microsoft is spending, around 80% of that is CapEx, and 88% of the CapEx is compute. It's very large. And then another 10% of the TCO comes from power consumption itself. So these are really large numbers, very, very large numbers, and it's a very big problem for the industry. Has to be addressed in the compute level itself, but also how we build the software, numerics in the software, whether it's 16 bits, 8 bits, it's always moving now from 32 to 16 to 8 to 4. That helps power consumption, other methods in terms of both training and inferencing. So all of these things just have to come together to solve the problem, but it's a very big problem.
So you have taken a very different approach in your companies, Sagence AIs, to compute, right? So could you elaborate a little bit on how you enable such low power compute?
Right. One big impediment for AI compute across the board is data movement between storage and compute. And that's where the CUDA cores and all, everybody talks about CUDA and all of that. That comes from the fact that you have to manage many, many CUDA cores and data movement between storage and compute. We've kind of scuttled the problem. What we've done is we've collapsed compute and storage into one unit. And then we have made that one particular transistor very dense, meaning we store a parameter in one transistor, which is normally stored in 48 transistors plus. So it's very dense, and then we use the same transistor to do compute. So there's no data movement between compute and storage, right? So it's a fundamental different approach, and that's one of the things that's really good with corporate VCs, because corporate VCs, as the topic of the day is, matters, corporate VCs really have a larger broad-term perspective. They are not looking to invest and then get a return within 5 or 7 years, as dictated by your LPs or your fund in a financial VC environment. And these technologies do take time to mature, to build, but they do make a very fundamental difference to the industry when they come about. So yeah, that's my 2 cents on that.
So Siddharth, what is your perspective from Samsung, and which is by itself a very hardware-focused company? So what's your perspective on these emerging new architectures, and do you think that they will be taking center stage for some of your applications that you're looking for?
Yeah, actually, I want to add to what Ankur was saying. And he mentioned a key point, which was programmability, which we don't talk about enough. So, last 4 or 5 years, we saw digital accelerators, then we saw what is called as near memory compute, then in-memory compute, digital analog in-memory compute. And we're talking about implementing entire transformers on ASICs. I think those are all steps in the right direction. But I would say, to some extent, this industry has not seen the success that it promised 4 or 5 years ago. And I think in large part, that's because of programmability. If you're an AI model developer, if you're an AI engineer, or if you write CUDA kernels, I think the entire ecosystem was built around NVIDIA. So there's Triton, there is VLLMs, all of them support NVIDIA to begin with. They don't support new ISAs. They don't support new instruction set architectures. But what happened with AI, or the AI moment in 2022, is that it spawned off a few companies. What are they doing? Is they're optimizing on 2 fronts. They're trying to democratize what is AI compute, as in, can I build a framework that an AI model developer writing on PyTorch doesn't have to change its code and can target to either an AMD GPU or NVIDIA GPU or some other accelerator built by one of the other companies. So there is that, companies that are building frameworks. And then on the other side, there are companies that are using LLMs to write optimized NVIDIA CUDA kernels, which I find to be fascinating. I think many of you followed the DeepSeek story a few years ago, and it talked about multi-headed latent attention. It talked about how to do reinforcement learning as opposed to supervised fine-tuning. But one of the details that was missed in that is what DeepSeek designers did is they programmed the PTX layer, the assembly layer of the NVIDIA GPU directly. So they removed all the inefficiencies, and that's how they got the performance per compute that they showcased to the world. And I think more needs to be done there. That's what I'm looking at these days.
Thank you. So having looked at different other architectures and whether they are better for one use case or the other, cloud versus edge, I want to actually touch upon energy. Vishal covered this a little bit. But I read somewhere that computing power needed for AI doubles every 6 months. So this is certainly becoming a bottleneck for AI data centers to scale. How do we address this growing energy footprint of data centers and make AI a little more sustainable? By sustainable, I mean sustainability from an energy perspective and from a cost perspective. And whether things like better networking architectures or better packaging can actually help along these lines. Maybe we'll start with your thoughts, Ankur.
Sure. So in terms of optimization for power consumption, people are looking at it both from a supply perspective as well as the consumption perspective, right? So on the consumption side, like you pointed out, there are multiple ways to optimize the power consumption. The underlying approach is system level thinking. Instead of pulling together a chip, a interconnect, a packaging, and the power infrastructure, hyperscalers and other data center builders are actually building all of this together, right? Optimizing for price, performance, and power, right? So they're trying to minimize, like Vishal was saying, within his architecture, he's basically doing away with movement of data from compute and storage, right? If you were to amplify that approach and apply it to a cluster of GPUs or a cluster of racks, companies are trying to minimize the data movement between GPUs or among GPUs, right? So there are innovations in optical interconnects, in chip-level connectivity that are minimizing data movement and associated power consumption as well as power loss or heat production for that matter, which has ramifications in the kind of cooling techniques you have to use, right? So that's one. Densification of compute itself is resulting in low power consumption. So instead of having thousands and maybe millions of GPUs, you're trying to densify it and use chiplet technology, 3D stacking of compute to densify the compute and minimize power consumption. And then on the power supply side, there are innovations around solid state battery technologies to smoothen the power requirements, right? Because data center power consumption is very lumpy and it fluctuates very fast in megawatts within milliseconds. And that puts tremendous load on the energy infrastructure. And as Vishal was mentioning, maybe I'll let you cover that point. I won't steal your thunder. But yeah, I think there's just tremendous opportunities to optimize power consumption even on the supply side. That's an area where I think our team at TDK Ventures is spending a lot of time. We have some investments in that space, but that is generally a very overlooked area by corporate VCs or VCs alike. I think there's so much more to be done on the power delivery and power consumption side. Yeah.
So Vishal, actually, that's a good segue to asking you. So I used to work at NASA, like it was mentioned, and when they had to test the wind tunnels, they had to actually inform the power unit because there's going to be so much consumption during the testing period. We are kind of seeing similar situation with AI data centers, but it's not a steady state power, right? You can't say, oh, everybody is coming home at 6 o'clock, and so they're going to turn on the lights, and so there's going to be a peak in the power. So it's not like that. What is your opinion on how this kind of variation in the power can be managed?
So has to be addressed from all different angles. At a fundamental level, the core of the problem, the heart of the problem is the compute. That's where all the power consumption is going, and data movement. I include data movement in that. So if you look at the power consumption that's happening in a data center, 60% of that is just happening in the compute node, which is also inclusive of data movement within a processor or GPU. But the other 30% is coming from external memory access like HBM and all of these memory. So memory access, if you look at it, 50% of 60% and another 30%, most of your power is really memory access movement. So that needs to be solved at a heart level, right? That's the core of the problem. But really at a system level, where to Ankur's earlier point, that it's all about data movement, like is what I'm talking about. And at a system, you have to look at it as a system level, holistic level as well, because you can have methods, even when you're mapping networks, you can ensure that the networks are sharded and mapped in a manner that the data movement from your external memory to your GPU, and also between different cards in a server or different servers in a rack, is minimized to a very substantial. So there's another layer of software that kind of manages that, and companies are looking at that as well. That also allows you to kind of manage the peak power consumption and how you're going to move it across all the racks that are available in a data center. So a very system level approach needs to be looked at and is being looked at, but also because even just 2 years down, 40% of the Data centers are supposed to be starved of power, in 2 years from now, which is not too far away. So we have to also really build out technologies which are orders of magnitude lower in power consumption, giving the same performance, to the point that it is now time for the industry as such to look at fundamental new technologies like, something like what we do, multi-level, deep subthreshold, compute within memory cells, near memory compute, all of these neuromorphics, all of these have to come about over the next, several years to solve the problem at a fundamental level.
Siddharth, what has been your approach to kind of answer this challenge, and what are you looking as vision where you think investments would really help scale AI?
Yeah, so I would say we were just having a discussion here about using photonics for connectivity. Many of you were probably at the NVIDIA GTC Summit earlier this year. So we had the silicon photonics CPO moment for the scale-out network, which was great. And I hope to God that we have the same moment for the scale-up network, which is coming next. So there is that, and all the innovations there drive efficiency in terms of power. So that's all I have to say about that. But beyond that, I think there's a few different things that we've seen in the last few months, which is, the traditional data center would be, you get 20 kilowatts in, and then something converts it to 480 watts, and then there is an AC to DC transition that happens to 400 to then 48 watts, and then 12, and then 6, and then to the chip, which is at 1 or 0.8 volts. NVIDIA recently announced this new paradigm where they wanted to deliver 800 volts directly to the rack. One of the things that will be enabling that is, of course, solid-state transformers. So there is that. So that's an area that we'll have to focus on. What it also does is, of course, all of these transitions that were traditionally happening in the data center, you've got 95 to 96% efficiency anytime this transition happens. But when you take it overall over 5 or 6 different stages, you lose a lot in efficiency. So perhaps SSTs can really make the transition directly to an 800 volt directly onto the rack, make that happen. So there is that. And then, of course, power FETs, wide bandgap materials for power FETs, all kinds of innovations happening within that domain as well. And the other is, of course, the chip sizes are growing, like reticle limits are being pushed, or people are talking about wafer scale engines, but you still have to provide power to those systems. And the only way that seems viable today is to do vertical power delivery. So companies that are building vertical power delivery solutions that, where you don't have to traverse a large distance in copper from the sides. Instead, you go up through the substrate and provide power directly to where the device is. I think those 3 areas are next up for innovation.
Thank you. So we kind of covered 2 rather important areas for potential scaling other chip architectures, challenges with energy. Very short, since I maybe hope to take 1 or 2 questions from audience as well. But in short, could you explain how CVC, as Samsung maybe, has kind of helped some of these startups scale? Because we are hoping that going forward, when startups, and I'm sure there are a bunch of startups here, they would look at CVCs as well as a syndicate partner for the kind of other than capital support that they can provide. So do you want to highlight something?
Yeah, so I should give kudos to TDK Ventures. You guys do a great job. We're not as good with our activities in boosting up the ecosystem. One of the things we do say we provide is we provide access and advocacy for every startup that we come across that we find interesting, whether it's a portfolio company of ours or not. And hopefully, Samsung is a very large ecosystem. Hopefully, there is a natural fit or natural home for one of these startups. We run, a bunch of semiconductor CVCs run this thing called Startups in Semiconductor Sustainability, an event that's an annual event where we invite companies who are in startups who are innovating within sustainability and semiconductors to pitch, and then finalists are given a spot in Semicon West every year. But before that happens, the semifinalists, we choose about 30 of them, they get access to corporate VCs and then their parent companies, resources within that, and hopefully we provide enough value through that process. So we'll keep running that program once a year. So that's my one anecdote of how we provide some value to the ecosystem. We can always do more.
Thank you. If in 30 seconds you have to mention something, Vishal, and you work with both VCs and CVCs.
Yeah. I think it's a good idea always for a startup to have a balance of investors, because financial VCs will look at it in one way. They're looking at it from a financial cash out point of view, and they will encourage you to how to do a IPO and/or an acquisition. So those things are important in their own respect. While CVCs are looking at it differently. They're looking at how does their company acquire a technology, number one, and how their company acquires new market access based on their technology. And both of those are lined up, right? So CVCs will really give you R&D access for their product, a lot of knowledge access, a lot of market access, distribution channel access, and when you do scale, they will guide you along the ways of how to scale your supply chain and so on and so forth. Longer term view, but really helping in terms of operations of the company. Each investor comes with their own set of knowledge base and advice to entrepreneurs, and it's always a good idea to have a good balance between the two.
Ankur, your 30-second view on this.
We're fundamentally a deep tech investor bunch at TDK Ventures. Tech or deep tech or hard tech is in our DNA. We have several PhDs along with Geetha in the team. So we really empathize with founders that are solving hard tech problems, dealing with physical sciences and helping them scale and create impact. We do this by bringing what we call TDK goodness to our portfolio companies. And that's in the form of making connections with various TDK business groups, go-to-market support, helping them with fundraising, hiring, marketing, and communications. Those are some examples. And we also organize an annual portfolio summit for our portfolio companies to get together and cross-fertilize ideas, not just amongst themselves, but with the ecosystem as well as with TDK execs.
Thank you. So if you could take maybe one or two questions from the audience. Okay. All right. Let's take one.
Hello, panel. Nice discussion. We are an edge AI company, and I wanted the view of the panel on whether we should include the PVT data or any data coming out of the probes from the chip that will help the application understand where the fault lies. Something similar to the Meta's paper of cores that don't count.
Siddharth, can you take it?
So I think you said you're an edge AI company, which...
But we want to include the chip data, the probe data from coming out from the chip, like PVT or anything else we can take and include in our decision-making process, whether there is a fault with the chip or whether it is the fault with something with the software.
Yeah, look, I don't know how much information you'll get by just providing, the PVT data that's coming out of the edge of the chip. For us, I think everybody's mentioned primarily comes down to inferences per seconds per watt.
Okay.
Or people call it tops per watt, but if you're wasting tops not doing anything, it really is useless. So let's say inferences per seconds per watt. So, right. I anchor in on that.
The question is, if there is a bug or there is an error in the process, whether it's doing an inference, whether it's doing a function call or whatever it is, we want to identify whether it is a hardware problem or a function problem. There's a bug in the software or there's a bug in the hardware.
So can I ask you just so I
Sure.
can just clarify, get more clarity on the question that you have. You're asking whether the PVT data is important to debug the issue?
Exactly.
Or yes, it is, and it depends on the nature of the bug.
Okay.
Because the PVD data tells you the reliability of how your process will yield over time, and the bug can be very yield related. But really depends on the nature of the bug. So you really have to look at, is this bug seeming like, for instance, let's say you run silicon and your typical silicon is always showing good results. But when you run a corner lot, you are suddenly seeing the bug appear. Obviously, that's an indication that it has to do with some kind of process marginality, which would come out of PVD data. And so then you dig into that, and then maybe you look into even TEMs for the process and so on and so forth. But the first level of analysis sort of lands you whether it could be in the software, whether it could be in the firmware of the chip, or whether it could be something that's yield and process related, right?
Yeah, that's exactly what we want to give to our customers.
Right.
Okay.
All right. Thank you so much, panelists, for an excellent set of discussions. Let's give them a round of applause.